In this video, we're going to look at another example of a Taylor series free response. This one's a little bit different. It says the derivatives of f of x at x equals 0 are given by this. So this is not the series. This is the value of the derivatives. So if you wanted the function's value, you'd plug in 0. If you wanted the first derivative's value, you'd plug in 1. If you wanted the second derivative's value, you'd plug in 2, and so on. So, remembering that a Taylor series, let me just write this down as I do on almost every Taylor problem. Okay, we do the value of the derivative at the point we want, x minus the point to the nth power over n factorial from 0 to infinity. Okay, so if this is the value of the derivative, I'm going to substitute that in right here. So we're going to have n plus 1 factorial divided by 3 to the n. Okay, and again, that just is this piece right here. Then I have, it's at 0, so it's, x minus 0 to the nth divided by n factorial. Again, that's just doing this piece. Okay, maybe I'll color code this. So the red part is the derivative, the blue part's the rest. Well, let's do a little algebra here. Of course, the factorial stuff cancels. We're left with n plus 1. X minus 0 is just x, so x to the nth over 3 to the n. Well, look at that. We got it. That's part A. Okay. So we have now shown that by plugging that derivative in place and doing some algebra, we are able to show what the series was. Now the next thing is, what is the radius of convergence? So, okay, we've got to do a little algebra again. We're doing the limit as n approaches infinity. We're setting up our ratio test. So we're going to have the n plus first term and multiplied by the reciprocal. Remember, it needs to be less than 1. So we do our algebra. Okay, we're going to have a 3 left on the bottom. We're going to have an x left on the top. I like to take the stuff that doesn't have an n and yank it out front. Okay, so that means this becomes x over 3 multiplied by the limit as n approaches infinity of n plus 2 over n plus 1. We need this to be less than 1. Well, what's inside here is 1, right? The limit is 1. So we end up with x over 3 being between negative 1, let me just kind of block this off here, and 1. So if we multiply, we get negative 3 and x, like that. You should check the endpoints to make sure that they don't make it converge. They won't. So this is our interval of convergence, so our radius would be 3. To integrate this term by term, I'm going to start by rewriting it. We have n plus 1. Instead of x to the n over 3 to the n, I'm going to write x over 3 to the n. So remembering that plugging n plus 1 in, this would just be a constant. How I would do the integral is I'd raise the power of this, so it would become x over 3 to the n plus 1 divided by n plus 1. And I already have an n plus 1 out there, so it looks like that. And then I have to multiply by 3. And if you're kind of confused where that comes from, think substitution. If u is equal to 1/3 x, du would be 1/3 dx. So to integrate, I'd have to multiply by 3. So my integral is 3 multiplied by x over 3 to the n plus 1. So that's the series for the integral of f of x. Now the next thing is, it says use it to show that 3 over 1 minus x over 3 is the antiderivative. So essentially showing that this is equal to that, because we've already found the integral. Well, this is a geometric series. So when it says, show that they're equal, I'm going to find the sum. So let's plug in the first term, or let's plug in 0 to get the first term. So we have, something to the first, but it's 3 times, x over 3. So it's 3. And the common ratio is x over 3. So this is the geometric sum.